Figure capital A dot 2 derivative and slope. The slope of a function between x sub 1 and x sub 2 is equal to the slope, open parentheses, equals rise over 1, close parentheses, of a straight line connecting the 2 points. B equals, open parentheses, x sub 1 and f of x sub 1, close parentheses, and open parentheses, x sub 2 and f of x sub 2, close parentheses. If we fix one of the points, B, and move the other point closer, then the run, open parentheses, h minus x sub 2, then the run, open parentheses, h equals x sub 2 minus x sub 1, close parentheses, grows smaller and smaller. If the derivative exists, the rise f of x sub 2 minus f of x sub 1 equals f of x sub 1 plus h minus f of x sub 1 will eventually get smaller as well, but typically at a different rate than the run. The limiting value of this slope is the derivative, which equals the slope of a line tangent to the function at b. If the derivative of f of x with respect to x is positive, the function is increasing at x. That is, as x increases slightly, the function evaluated at x also increases. Similarly, if the derivative of f of x with respect to x is negative, the function is decreasing at x. One problem with using derivatives instead of slopes is that in some circumstances the derivative of a function may not be defined because the limit given in equation capital A dot 2 does not exist. Discontinuous functions do not have derivatives at any point of discontinuity. For example, the derivative of the function 1 over x does not exist at x equals 0. The derivative also fails to exist for a continuous function at a kink, such as at x equals 0 for the function the absolute value of x.